I won't delay too much to be of this, but we're going to do Rui Teixeira. My accent is great. So, I'll hand over to the civil engineering lecturer in structural engineering, joined around 2020 at home. So, and it's also part of the DBIC program, bringing them over to collaborate and teach in Chang'an in China. So, we're great to have them here then today. So,
thank you. Well, first of all, thank you for the opportunity to be here and present some of the work we are doing last years. Today my name is Rui, of course, I'm going to talk about rare events in engineering systems, and mainly how can we better understand and prepare for such, and we call them drivers. Just to give a bit of context, so professor of civil engineering. Most of my teaching is in structural engineering and systems engineering, and my research interest mainly on risk and reliability, and mainly applied to structural systems. So, since I'm here, a good opportunity to talk about some major projects. So the first one is CERTO. So it's a research innovation action that is coordinated by engineering. So the other is people that is a challenge and leading, supported by SNEP and the environment. First of all, to visit the website, interesting projects. But again, I'm here to talk about rare event changes and why do we care so much about them? Care a lot because usually this is what happens. We have disasters. So this is a very famous, not in a good sense, structural failure that happened in the Charles de Gaulle airport in France, 2004, so not that long ago. That is what we call lack of robustness. And again, the origin was a rare event. And even considering that we call them rare events, they occur more often than what we expect. So, see them everywhere, and usually they result in these disasters, okay? And we don't want them. So, I see someone knows this one. Why are they so challenging to work with? Because usually, if we think of the, distributions of the uncertainty in different variables that we can have in a system or in the output, they're usually there. Okay, so they are in this, we call them details. But they don't occur, they are called rare events, they don't occur very often, right? So a good way to think about them is, let's think of an orange, okay? We have an orange, certain size, and we want a rare orange, and the rare orange is going to be the big one, right? So let's think of the size still. So we want the rare orange, and we start, and we go to the supermarket, you start selecting, we do that process of picking the different oranges, trying to find the big one, and we're all happy we got the big one. Okay? That's great. And that's a rare event, because it was the biggest that was there. So if we would look at the probability, if there were many oranges, there would be, in the tail over there, you can see the red dot. However, when we work on this process, we do see also that sometimes we are just picking a normal, an orange that is not that rare, and then one falls in the ground. Okay? So that's also rare. We will expect that. Then we don't want to put in the ground. So that's, that's kind of a failure for us. So this is why it's so challenging, because there's this complex process that sometimes originates things that we don't foresee before we work with them. And if you think of an engineering system, and I'm going to talk about wind turbines, because there's something I know well. So we think of the waves, wind, this is installed in the sea. There's also things happening. We have a tower, there's a control system. We are generating power at the same time. And so this system can get really, really complex, right? So just think of the waves. You look at the waves, they seem so random. So many things happening in the sea, there are waves. And so if we would, try to describe this with multiple variables, what we would see would be something like this. Okay, so variables everywhere. Our brain is not good seeing good in high dimensions, so very difficult to cope with the level of complexity. And if something happens, it just propagates through the whole system. And that's what happens usually, or what has been happening with engineering, systems and other subsystems. They are becoming very, very complex. So just, we use a lot of, we call these very heavy computational tools. They allow us to make decisions. They are great. Some of them will take 3 hours in the computer to run, 2, 1 hour, 6 hours. I mean, worked in some projects, we needed 24 hours to analyze a certain code. And if you think of lab experiments, that also give us a lot of insight. So, there's only a limited amount of things we can do in the lab, right? So if you're lucky to have the capacity to do the same experiment 10 times, just to see what's the level of uncertainty we may have. And this is, of course, it's very difficult to find that rare event, that picking that orange that falls in the ground if we only have this setup, right? So what we have been working on for this is to start thinking of this as a dual problem. We have complexity and we have effectiveness. And we think that the combination of both allows more insight into, looking at the system, engineering system, structural system, that gives a bit more insight on the kind of things that can happen. So usually we refer to high fidelity, low fidelity, and things that are low fidelity would be very, cheap to analyze, to do, and will give, probably the results are not great, but they still allow us to see something into the system. And high fidelity would be that 24-hour code. We think that is the most realistic. We can get real data with the high fidelity, and that allows us to understand that the system is very high accuracy. Okay, but usually they are very costly to get. That means, time, money, so difficult to do many repetitions, and to try to find the spectrum of things that can happen in the system that we are trying to analyze. And just to give a bit of context to this, I'm going to describe 2 examples that we worked very recently, and that can give a bit of insight of how this may look in practice. So this is just, the level crossing with, I think all of us have seen it in our lives. It's, we use them to cross the railway with the road. And we were analyzing this because they may seem rare, but they are everywhere in the network, and they have problems of degradation. Okay, so we started to analyze that, and we wanted to look at the lifetime behavior of these things, and we created a very high fidelity model. I think it took 6 hours. We assumed that it was very realistic. It's not this one, just a representation. And when we saw that it was going to take us 6 hours to run this, we said, okay, there's just so much we can do with this. So if you think 6 hours to on a very high fidelity to run this, so that would be 4 evaluations per day, 3 days, you can do 12. That's not great. So we decided to create another slightly lower fidelity model related to that one that will take a couple of minutes to run. Okay, and it worked quite well, but still was not enough for us because minutes was still too much. So we decided to go to another one. It was a surrogate, and we started to work with the tree. And the trick was to only call the higher fidelity when we need it. Okay, so we didn't want, only when it was strictly necessary, we go and we check if the results are going well. And we started to use this, for instance, and this would be an example, study the sensitivity of the extreme. So we didn't want the sensitivity of the normal behavior. We wanted the sensitivity of the rare events. When we designed this, there's so many variables. I wanted to see which one is more important in terms of the extreme events that then is going to make an impact in the degradation in the lifetime behavior of this infrastructure. I also had here this example that was, I think, was a very good example of how empirical knowledge can build with time. So the other thing we did with this was to run a multi-criteria optimization on minimizing the extremes. Okay, so we wanted a design that doesn't experience very extreme events. Okay, and what we saw in these multiple criteria, there were 4 criteria, is that there was this green one over here. That was the reference design, the one that was given in the standard. When we saw the results, we were like, wow, someone must have, at some point in the design of this, fund an optimization on all these criteria because this design is so good, right? It's so balanced, but so balanced. And I think we tried to check for that. We didn't see any background documents, so we assumed that that was just, you know, knowledge built with time, empirical knowledge. People just improved every time they designed a new one until they got that. So it's a very, very interesting example of empirical knowledge can build with time and create very good solutions. The other example I would like to talk is just to give also an idea of, so here we are talking about sensitivity. We work with these three fidelities, and we see the sensitivity of the different variables to the extreme events because we want to control them very well. And the other example that I'm going to talk about is this small city in the south of Spain, very vulnerable flooding. And we also wanted to check the adaptation of this. There were 30 something measures of 37, if I'm not mistaken, measures of adaptation, different contexts. And we wanted to check, you know, a probabilistic. We wanted to make a probabilistic informed decision of the adaptation. So that would be an optimal decision that would minimize an expectation of risk. Okay, that would be the damage or the cost. But we also wanted something else. We wanted low expectation, but no surprise. Okay, because sometimes you minimize the expectation of certain cost, but there's a certain chance that you may have a surprise, you know, and your cost is going to be much larger than what you think. That's certain, right? And we saw something really interesting. So we started to. So what we can see here is that. You know, would be a certain solution, and you can see the solution because it's uncertain. What may happen in the future is uncertain. The solution spreads over a certain probability. That's the cumulative distribution function, an empirical one. It spreads over you know, a certain amount of cost, right? So it can have 20 to 80 million costs. That's very large uncertainty there, and we started to see different solutions. And when we started to optimize in different criteria, what we did was, okay, we have the expectation here. And let's say this is no surprises. Sometimes a measure of, you know, certain solution will have low expectation, but could have large level of surprise. That would be 1% chance that we are going to have more than twice the cost than what we expected initially. And what we did see, and it was very interesting to see, and this idea of working with different, you know, so we had a very surface runoff model here. We had another surrogate. We had a couple of combination of data there. Is for instance, if you look at these two solutions, they have a certain level of expectation, right? So there are about 30 something million, or I'm not sure if this is, yeah, million euros, but one of them is, you know, has a much larger level of, you know, surprise, right? So I can be here, I have 30 million, and with 99% confidence, I can say I have less than 60 million damages. You know, the solution is very, very narrow. But here I have, you know, 1% of chance that I'm going to have more than twice of the cost. And if we would decide only on the expectation, we would pick the one that has a very large level of surprise, right? So this is the kind of insight you can get with this. So I would pick this one if I decided only on expectation. But then there's a certain risk that in the future I'm going to have a surprise and I'm going to spend 3 times the money. And the difference from here was just most of it was invest. If I invested a bit more, we'll have a much lower surprise level. And I mean, also take this opportunity to talk about the Center for Critical Infrastructure Research. So invite you all, if you're interested in topics of critical infrastructure or topics related to this, feel free to join us there. And yeah, we have a Twitter, we have a website, so feel free to go and visit what we've been doing. Okay, thanks. I don't know if you have any questions.
And we'll hand it over to the floor. Anyone have any questions on that? Keep to a couple of questions.
All right, that was really interesting. Computer models you use work, but is it similar in any way to an adaptive route where you're your high resolution models being used with where there are ratings regarded.
Yeah, it could be. So mainly that would be the strategy, would be you. Yeah, there's if you're comparing the two models, there will be a certain level of uncertainty. Is that okay? The prediction that is given by the lowest fidelity is not good enough. We should trigger the higher fidelity to calibrate that. That's it's kind of adaptive learning strategy. Yeah. Okay.
So the next slide, okay. So so the probability of extreme seems to be the same kind of line. It is increasing with the expectation. Both of them.
Now, because this is the full cost. Okay. Well, I mean this one.
So if you have an optimization, you can expect generally one would have a negative slope and the section will be optimal. So in this, let's say if you have an expectation as well.
It's okay.
So the expectation is also included. You know, also included. So if you have a larger expectation, so you have another extreme as well, which is so.
Oh, yeah. So from a point of view, this is a cost. So it's not total cost. So if the expectation is larger, that means the extreme is going to be the expectation. So the distribution is shifted to the right of the cost.
So if you look at the development, this is the graph of the extreme, this is the graph of the expectation. So exactly, and the optimum is.
Now you're searching for the intersection, but this is the correct. This is there's a multi-criteria representation. Not trying to find the balance between the two. Okay.
Gustav, what's your principal area of patient? So you're also engineering,
Yeah.
work with other people.
I mean, most of my work would be much of my work on risk of marine structure in the past. But yeah, I mean, then we started to see there could be there's synergies in this area of risk for welding because these models are very heavy to run most of the time. At least on a larger scale because something is going to happen far away, it's going to local scale. I mean, this is an example of the kind of complementarity. But should be probably more applied probability. Mainly to structural and physical. So we work often transport networks or that's just some example of kind of things. Yeah.